Okay, so I structured my presentation to kind of mirror the structure of the session that Jason gave us at the beginning. So I'll start talking about available assets and then focus on needed assets. In terms of available assets, I'm going to talk about the Kinematic Atlas Initiative, which is a multi-center effort to establish new standards for data sharing in biomechanics and to work towards a field-specific research environment to allow the secure sharing and processing of human movement data, using especially a federated data model. So even though this idea of having a dedicated data sharing platform for our field, it's not really new, right? They've already been doing it in other fields like in genomics. What motivated us to pull the trigger now and go for it in the human movement sciences were the new opportunities that data harmonization tools like Reframe, for example, now offer us. So a little bit more about Reframe. Reframe is short for Reference Frame Alignment Method. And of course, I invite you to read the full publications, but very briefly, Reframe is a post-processing method that achieves harmonization of coordinate systems through optimization. So a user-selected cost function is minimized by varying only the local segment frame poses. So the orientations and or positions of the coordinate systems that you see here on the left relative to the underlying bones that they represent. By optimizing the segment reference frames of different data sets with the same underlying cost function, we're effectively targeting a consistent set of reference frames across our data sets. And the concept is really kind of similar to what we're already doing with functional flexion axes, for example. The main difference is just that the user is free to select their own cost function and that we can harmonize and optimize in all 6 degrees of freedom. So why is ensuring consistent reference frame poses so important? Because if we take 2 knees, as the ones that you can see here on the screen, that are moving in the exact same way, have the same bone geometry, but then we use reference frames that are only slightly differently aligned to quantify those kinematics, we're actually going to end up with signals that are visually different, even though we know they represent the exact same motion. And the magnitude of the axis differences that you need to have that effect is actually not big at all. It's like 1, 2, or 3 degrees. So this is a video that a colleague of mine, Ariana, put together. Here you can see the reference frames orientation are changing by up to 3 degrees maximum around any one axis. Look at that variation, right? So there's offsets in the curves, there's a peak becoming a trough and vice versa. That's all the same motion. But by optimizing different data sets based on the same underlying cost function, we can effectively remove any differences in the kinematic data that could plausibly be associated with reference frame inconsistencies in all planes and in all degrees of freedom. We validated this model for the tibiofemoral joint using 6 degrees of freedom fluoroscopy data. And as you can see, Reframe did lead us to convergence in the signals and in the reference frames in all 6 degrees of freedom. So you only see the green lines after because the 3 are perfectly overlapping. So essentially, after applying a reframe, you can much more confidently say that whatever differences you see between your signals, it could not possibly be due to reference frame inconsistencies. And therefore, the hope is that they're coming from a more meaningful source, right? But we still need to look into that. We've also used Reframe to compare different data capture modalities like IMU versus a robotic joint simulator, marker-based versus markerless, 5 different marker sets. And as you can see, Reframe suppresses a lot of that signal variation that was plausibly not relevant. But anything that cannot be associated to reference frame differences will and does remain, with the added benefit that it's a much more robust indication of potentially real clinical changes or differences. So with that in mind and this opportunity that Reframe gave us, we thought, great, so now we have a new tool that we can use to compare kinematic data sets. It eliminates a big source of variation between data from different sources. So it motivated us to start the Kinematic Atlas initiative. We're still very much in the early stages of this, but we're currently focused on achieving 2 main goals. So number 1 is we're trying to establish new data sharing recommendations, which we'd ideally like to be ISV recommendations. We have a drafted summary set of recommendations, so it's not the full background document with the reasoning behind the recommendations, but just the recommendations themselves, which you can see through the QR code, and please give us your feedback on that. We're also trying to refine a concept for a trusted virtual research environment that's dedicated to the exchange of human movement data. So towards our first goal, like I said, we've published the draft of the summary recommendations, and a little over a week ago, we had 2 sessions at the ISB conference in Stockholm. We gathered community feedback on, using systematic polling and interactive discussions on questions like, how satisfied are you with the current data sharing landscape? What represents the biggest hurdle in sharing data yourself or using data shared by others? And how should industrial partners engage with the data repository? We've gotten up to 95 responders per question, and now we're compiling a summary report that we hope to make publicly available towards the end of the year so everyone can go through all the answers. Towards our second goal, we've been working with a data analytics expert who has previously built research environments for the NHS in the UK. So it's really someone who has years of experience doing these kinds of projects. Coincidentally, and thank God, because he's actually the brother of Professor Dominic Thulis in Adelaide, he's doing this at virtually no cost. So we're getting his services at essentially no cost, other than the cost needed to run the environment itself, which is really an amazing opportunity for us. So this is kind of where we're at in terms of what assets we have or that we're working towards. But the next question is, of course, what is still needed? And when I was making this presentation, I kind of sat down and thought, okay, assuming that we get all this to work, which will be a big enough challenge as it is, but assuming we get it to work, what would still be missing? And for context, my background is actually not modeling at all. It's more gait analysis and trying to bring motion capture into clinical setting. But in my perspective, and to be fair, this is just want to acknowledge my research partner, Ariana, because he's a mathematician and his mathematical, logical way of thinking has really been crucial to reaching this conclusion. But after a lot of philosophical discussions, our perspective is that what we're missing right now is a way to identify clinically relevant intersubject differences. So in simple terms, we need a way to compare subjects. So why is this such a problem? At a very high level, axes are going to be either functional or anatomical, right? So either based on motion or based on anatomical landmarks. So if we look at functional first, a lot of the times functional axes are recommended because they quote unquote reduce crosstalk or minimize crosstalk, and also because they're supposed to be more repeatable, right? Because you're finding them using a mathematical equation, you're optimizing, and so you're removing a lot of that human error related to marker placement, and inconsistencies between evaluators. So while that is true, the problem here is that those axes do not have a clear fixed relationship back to the joint's anatomy that's going to be constant across subjects, right? It's going to be different for each subject. So in theory, you could end up with signals that look the same, but for whom the orientation of the subject's functional axis is actually clinically different, and that's a clinically relevant difference. So the figure is obviously an exaggeration, but you get the point. Otherwise, we have anatomical axes. And here we'd rely on the position of bony landmarks like the epicondyles, right, to define our axes. Here you will have some crosstalk like that, right, just because of the nature of how we're defining it. But there is the added benefit that assuming you identify the landmarks correctly, there's an anatomical consistency in how those axes are defined between subjects. The problem is that no two human beings are the same ever, right? So no two people will have the exact same natural bone geometry, which means that just because of natural anatomical variation, no two subjects will have their axes inherently aligned or oriented in the same way. And honestly, we can't even assess that because aligned relative to what, right? We need some kind of objective absolute reference frame that has to be consistent across all humans, or at least across all healthy people or something like that. So we'll inherently have differences in reference frames across subjects if we use anatomical axes, but functional axes also have problems. So the problem is right now that, the signals for anatomical axes might look different, even though they're actually representing the same motion. And this is where I think we're a little bit stuck at the moment. So we do have ideas on how to tackle this problem. One of the most promising ones relates to flipping the problem. And instead of looking at the signals, maybe focusing on where those axes and those origins go after something like reframe relative to the bones. So we presented some of this work about a year ago at the ESB, and we showed how we were focusing on qualitative differences in frame position after reframe to inform whether, for example, a total knee arthroplasty patient should get a medial stabilized implant or a different design. I think this is something also like a place where statistical shape modeling might be useful, especially in terms of trying to define some kind of average or universal reference frame against which to compare. So we do have some ideas, but in my opinion, this is where the key challenge really lies. And that's not all of it, because that's assuming we can do this based on medical imaging. What do we do in the absence of medical imaging? Because at least in my area in gait analysis, most gait analysis studies don't have medical images. They're doing, marker-based, marker-less IMUs. They don't have CTs, X-rays, or MRIs. So what can we even say about the kinematics then? I'm not really sure yet, to be honest. Oops. So I hope that wasn't too demotivating, but rather I just wanted to highlight some fundamental questions in our field that I think are still open that we critically need to address. And so whatever new assets we come up with, we really need to keep these important challenges in mind.